Hello everyone, welcome to another video on the channel. So today we're going to go through the oxyhemoglobin dissociation curve. And what that is the curve that's analyzing the amount of oxygen that we're taking up and holding in our blood cells. So here, let me pull up this presentation really quickly. So for the oxyhemoglobin dissociation curve, what we are trying to analyze is how much oxygen is actually present in the hemoglobin at a set period of time. So in a tissue level, we're going to have very low oxygen because we have dumped all that oxygen off and it is now being used for metabolism at that tissue. So the percentage of oxygen saturation of hemoglobin at the tissue level is going to be very low, about 40 millimeters of mercury or so. At the alveoli level, which is the level at the lung where exchange is happening with the capillaries and the atmosphere, we have about 100% or so of oxygen saturated in the hemoglobin, and that is about 100 millimeters of mercury. So this dissociation curve is showing how much oxygen is given off between the time that it is bound in the alveoli and the time that it is given to the tissue and carried into the veins. So when we are going to have the physiological range, we're going to see that in the venous blood, about 40 millimeters of mercury or so of pressure is going to be where we're at. Even though we only have 40 millimeters of mercury of pressure of oxygen here, we still have about a 3/4, 75% of our hemoglobin saturated with oxygen. That means that 4 out of the 4 binding sites for oxygen at each hemoglobin are bound. So we still have a very high percentage of oxygen bound to hemoglobin here at this point. However, it is not nearly as much as we have here at the top, where it's usually about 98 or 99%. So for our first curve dissociation, here with the normal physiological range, we go from about 98% saturated to about 75% from the highest to the lowest point. If we want to change the amount of oxygen and how fast it's going to dissociate from our hemoglobin molecules, we can do that by changing a couple of components. Here in our graph, we see the analysis of changing of different components like pH. So if we increase pH and decrease the temperature, we're automatically going to cause less dissociation. We're going to have less oxygen leaving hemoglobin, even as we get down to lower oxygen pressures. So even though in the venous system we have 40 millimeters of mercury oxygen pressure, we're still going to have over 80% of our hemoglobin saturated with oxygen. So higher pH and lower temperature causes conservation of oxygen and binding to hemoglobin. The inverse of that, if we decrease pH and we increase temperature, as in we become more acidic and also we add heat, that's going to cause oxygen to come off more. So oxygen is going to dissociate faster from hemoglobin, and the hemoglobin remaining at the 40 millimeters of mercury pressure are going to be saturated only at about 65%. This is a toxic environment, all right? What these are called are the Bohr and Haldane effect. The Bohr effect is going to be where we have a decrease in pH, which is usually from an instance of increased carbon dioxide, and that is going to cause more unloading of oxygen because we have more carbon dioxide in the system than we need. The opposite of that is going to be the Haldane effect, and this is where we get oxygenation of blood in the lungs that displaces carbon dioxide. So the Bohr effect is going to be oxygen dumping when we have a low pH and high carbon dioxide. The Haldane effect is going to be binding of oxygen and oxygenation of hemoglobin when we have high binding of hemoglobin with carbon dioxide. So we have oxygenated blood has a reduced affinity for carbon dioxide. So here we're looking at a couple of different cases. If we look at a person who has an alkalotic state, right? If you're an alkalotic, that means that you are in a basic state. Your blood pH is up in a number, maybe towards 8, right? Maybe you're hypothermic. You're automatically going to have an oxyhemoglobin dissociation that's going to be bound much more. So the oxygen is going to be kept on hemoglobin at much lower partial pressures. So some of our examples down here. If we have an arterial blood that only contains 20 milliliters of oxygen for every 100 milliliters, that means that 100% of the oxygen, or the hemoglobin oxygen binding sites, are occupied by oxygen, all right? That's a very, very high percentage. However, in the venous blood, we only have about 15 milliliters of oxygen. So that means that even at this small change, 20 milliliters versus 15, that brings the percentage of oxygen bound to hemoglobin down almost 25%. So that change of oxygen pressure in the liquid is going to change the number of oxygen molecules that are bound to the hemoglobin. All right, and our final graph is showing what happens during hypoxemia, which is low oxygen or low blood oxygen. If we have hypoxemia, we are going to characterize that by how much partial pressure of oxygen there is in the blood. If we have a mild hypoxemia, that's where we have a partial pressure below 50. If we have moderate, it's going to be below 45-ish to about 30. If it's severe, it's going to be anywhere from 30 to 20, and then critical, which is life-threatening, is anything below 20. And we have to remember that that is in the venous blood, right? So the partial pressure of the lung, partial pressure of the oxygen in the alveoli, drives the partial pressure of the arterial blood, okay? So if the partial pressure of oxygen in the lung is going down, then the partial pressure of oxygen in the blood is also going down because more oxygen is going to be conserved by hemoglobin and bound, all right? So finally, if we have a partial pressure of oxygen that's increased, that means that the hemoglobin oxygen saturation is going to increase. So if we have more oxygen than we need, we're going to have almost 100% binding to hemoglobin at all times. If we have much less than we need, right? If the oxygen partial pressure is 0, automatically the hemoglobin partial pressure is going to be 0 because there is no hemoglobin molecule that has any oxygen bound to it. So for normal circumstances, our oxygen partial pressure is 100 millimeters of mercury in arterial blood. And at that circumstance, 100% of our hemoglobin is going to be bound to oxygen. This is normal. So lastly, remember, partial pressure of oxygen in our arterial blood, 100 millimeters of mercury, usually around 100% binding of oxygen to the hemoglobin subunits. In the arterial blood versus the venous blood, which is going to be around 40 millimeters of mercury. And we're going to have only about 75% of that hemoglobin completely bound to oxygen. So that was a short tutorial on the oxyhemoglobin dissociation curve and what circumstances, what diseases may lead to there being a disconnect or dysfunction in the ability of hemoglobin to transport oxygen around the body. Thank you all so much for listening, and I'll see you at the next video.